have Wienhard from Max Planck Institute for the Mathematics and the Sciences, Vidis and IS, who will talk about positivity representations and non-commutative hyperbolic geometry.
Well, thank you very much. It's a pleasure to be here. So it's my first time in Stony Brook, actually, and I really enjoyed it so far. So thank you very much for the invitation. So what I want to tell you about in my talk, there are two main players which interact with each other. So one is, which I denote by sigma g, is a closed oriented surface of genus G, and I assume that it has negative Euler characteristics, so G is bigger or equal than 2. There is some story for when the surface is not closed, but I will completely ignore it just to make things simpler. And the second player is G, a semi-simple Lie group. And I won't do, if you know semi-simple Lie groups and the theory, you can think about the general semi-simple Lie group, but later we will see several examples, and if you don't know this, I want you to think just of examples, and let me write down the main examples which will appear. So SLN, n by n matrix of determinant 1, SO PQ, so if you have an orthogonal form of signature PQ indefinite, and you look at the group of linear transformations preserving that, or the symplectic group. And I mean, there are more, but these are the main examples you should think of. So before I want to describe the general story I want to talk about, I want to describe a baby case and motivating example for you. And this as when we take the surface and where this semi-simple Lie group is just SL2R or PSL2R, which arises as isometry group of the hyperbolic plane. So first I want to shortly give you a picture of somehow hyperbolic geometry and hyperbolic structures on a surface sigma G. So for this, let me just recall one way to think about the hyperbolic plane, so the constant curvature -1 simply connected Riemannian manifold is to look at the upper half plane model. So we look at complex numbers where the imaginary part is positive. And there's a Riemannian metric on it, which is essentially Euclidean metric scaled by imaginary part of the point where you are squared. And the group of isometries of and I look at the orientation preserving isometries of the hyperbolic plane can identify with PSL2R. And so we'll always gloss over the difference between PSL2R and SL2R. So think of a just 2x2 matrix with determinant 1, and the action is given by fractional linear transformation. So A, B, C, D, phi to Z is AZ plus B and CZ plus D, the -1. Okay, so by classical uniformization theorem, under this condition, if we assume that the genus is bigger or equal than 2, this topological surface can be endowed with a hyperbolic metric. So it can be modeled as a quotient of the hyperbolic plane. So how do I want to think of such a geometric structure? So I want to think of it by separating somehow the topology on one side and the geometry on the other. So X will be H2 mod some discrete subgroup of PSL2R, so group of isometries. And then if we look at the quotient manifold, I assume it acts freely, it carries a hyperbolic structure. And so putting a hyperbolic structure on the surface, I think of having this hyperbolic surface, which comes, and a homeomorphism F from my topological surface to that. And so a pair of two such things, so a hyperbolic surface and a map from my fixed topological surface, there is what is called a marked hyperbolic structure. And so you can look at the space of marked hyperbolic structures. So these are these pairs X and F. And now we want to model by some equivalence relation, which essentially is what happens when I act by an isometry on this side, right? So what is the equivalence relation? So if I have two marked hyperbolic structures, xf and x prime f prime, I say that xf is equivalent to x prime f prime if there exists an isometry such that this map from sigma g to x prime is homotopic to this map f prime. So and that f composed with I is homotopic to f prime. So what is one nice, I just want to point out two nice properties or aspects from looking at this marking and modeling out by this equivalence relation. As one is if this marking allows me to really give names to curves on my hyperbolic surface. So if I look at this hyperbolic surface, I can, and I have a curve, I can give a name to it because again I can look at, okay, so this curve, what corresponding curve did I look on my fixed topological surface? And this is, for example, interesting. It allows you to, I might mention this later, to define nice functions on this space. The other nice thing is that on this space of marked hyperbolic structures, the mapping class group of the surface, so what this is homeomorphisms, orientation preserving homeomorphisms of the surface modulo those which are homotopic to the identity. This clearly acts on this space because I can just pre-compose my marking with a homeomorphism which is not isotopic to the identity. And because I require here that they are isotopic, I get a new structure. So this is interesting. And this is an object in mathematics which, I mean, it arises in many different contexts, and it's important to understand. And we, for example, still don't know whether this is a linear group or not, or whether it has a finite dimensional linear representation. This space has a natural action of this. And again, due to uniformization theorem, there's the space of hyperbolic structures is actually a model for the Teichmüller space of the surface, so the space of marked conformal structures or complex structures on the surface. And if you take the quotient by the mapping class group, you have a model for the Modely space of Riemann surfaces. So this is just to give a bit of context. And so now I want to add one more way of looking at this space, and then we go point out some properties, and then we go to this more general situation. So let me remove this so that I have a little bit of space. So I want to now, here we look at this space geometrically. So we look at geometric structures and some Modely space of geometric structures. So now I want to take a more algebraic point of view. And because I have this marking, I can remember from this hyperbolic structure just what it does on the level of fundamental groups. So if I get all the geometry, I just remember what it does on the level of fundamental groups. So I have a map which sends f to the induced map on the level of fundamental groups. What goes in? So what does it give me? I mean, it gives me a group homomorphism of the fundamental group of my surface to lambda, the fundamental group of this hyperbolic surface, but this naturally is a discrete subgroup of PSL2R. So it gives me a group homomorphism of pi1 of my surface into PSL2R. And because we mod out here by actions by isometries, this is well defined up to the action of PSL2R on the group of homomorphisms by conjugation. So where I take a homomorphism and then I modify it by conjugation. So this map is actually injective, so I can think of this space of marked hyperbolic structures or Teichmüller space as a subset of this space of homomorphisms. And let me point out two properties of this subset. Then in order to formulate this property, we have to think for a moment that this here is a nice topological space. So PSL2R is a Lie group, so it has a nice topology. The fundamental group of a closed surface is a finitely generated group. So homomorphism is defined by telling for each generator what matrix you associate. So you can think of this as being sitting in PSL2R to the number of generators. This space has a nice topology. Then you take, here you have one relation to satisfy, so you have this closed subspace which inherits the topology, and then you pass to the quotient. So this is a topological space. And this image of the space of hyperbolic structures is actually a connected component of this topological space. So it is a connected component. And points in this connected component have very nice geometric properties by the way where they come from. So they are induced from a hyperbolic structure. So in particular, the image is a discrete subgroup. And they are induced map from a homeomorphism, so it's an injective map. So every point in this connected component is an injective homomorphism onto a discrete subgroup, and this we call a discrete and faithful representation. So discrete and faithful. Okay, there are other nice properties which I don't want to. I don't have the time to talk about all the nice things. So this space has a very nice structure in its own. It is a symplectic manifold. This space even has a Kähler structure. There are certain dynamical systems on it. So there's a lot of rich things going on. And if you're interested in any of those, we can talk about it afterwards. So I don't want to focus on this here. So I want to really look at this property because this is in some sense now the thing which I want to discuss, and in the case of more general semi-simple Lie groups. So when we have this picture, here on this space, we look at group homomorphisms, right? We can take PSL2R and replace it by any Lie group whatsoever. It still makes sense. We can look at homomorphism of the fundamental group of my surface into any Lie group up to conjugation. And so we have this space which is called the representation variety. This again is very interesting space in its own right. So it parameterizes flat G bundles over the surface. There's some interesting, if you fix a complex structure on the surface, correspondence with the space of Higgs bundles. So it's a space of holomorphic objects on the surface. And, the symplectic structure gives you very interesting dynamical systems on it. You always have an action of the mapping class group on this space, which in some part is ergodic, in some parts it's properly discontinuous, in some parts we don't understand it. So there's a lot of, again, very, very interesting things of this space. What I want to address, and there's a question where I want to talk about phenomenon happening in this general case for general G, which is similar to having this picture which we see here for PSL2R, so in the case of hyperbolic structures. So do we have subspaces in the space of homomorphisms which behave similar to the space of hyperbolic structures on the surface? And let me give you some definition of what I mean by similar, and it's really looking at this property. So I call a higher rank Teichmüller space to be a connected component, or more generally, we'll have union of connected components of that, which consists entirely of discrete and faithful representations. And so this is, in some sense, really, how this whole, studying these objects came about. This is an a posteriori definition, so no one came up with this definition and say, oh, let's look for these things, but it's more people came up with things which have this property, and then you make this as a definition. Because if you start defining that, you might wonder, do you have a chance that these things exist at all? And the first case, if you think of, okay, so we generalize this, you might think about it as, okay, PSL2R, the next simple Lie group I know is PSL2C. So just replace the real by the complex numbers. And if you put a complex Lie group there for G, you will never find anything like that. Because for complex Lie groups, we understand very well what are the connected components of the representation variety. They all come from characteristic classes, characteristic numbers, essentially. And so basically for PSL2C, there are two components, those that live to SL2C and those that don't live to SL2C. And if you look in both of these components, there are clearly representations in there which are not discrete and faithful. So for example, in those which live to SL2C, you have the trivial representation. And the trivial representation is far from being injective and far from, has discrete image, but it's. So for complex Lie groups, we will never see anything like that. And so basically, so if you would make this definition, it's perhaps surprising that you see something. And as I said, the way the story goes is that we saw examples which satisfy this property. And now we know that there are at least and conjecturally exact 4 families of Lie groups, simple Lie groups where this appears. And let me just formulate it as a theorem which involves work of many people. So starting with Hitchin, Goldman, Choi, Fock and Goncharov, Labourie, then work with Mark Borger and Alessandro Iozzi, and then work with Bichard and Labourie, and with work of Beira and Pozzetti. And in the last statement I will make in this theorem with Beira, Bichard, Labourie, Pozzetti, and myself. So basically, let me formulate it in this way. So there are 4 families of higher rank Teichmüller spaces. And we call them higher rank because, as you see now in the families which appear, they are all Lie groups of higher rank, except SL2R. So let me give you the first family of Lie groups. So this is G is a split real Lie group. And so what this means is that if you look at the dimension of the maximal subgroup, which is diagonalizable over R, it's the same as the dimension of the maximal of the dimension of the subgroup, which is diagonalizable over C. So every complex Lie group has one split real form. I don't want you to necessarily think of the general case, so let me write down the list of classical groups which appear here. So these are SLNR, the orthogonal groups of signature NN, NN plus 1, and the symplectic group. And in this case, these higher Teichmüller spaces were first introduced by Hitchin, even though he didn't prove that they are higher Teichmüller spaces in this sense, and they are called Hitchin components. And I will give you explain a bit more how they look like in a minute. So the second family...
So is the correct component the one that comes from including SL2R into those groups?
Yes, exactly. So you take the irreducible representation, or more generally the principal SL2 in this group. And I just write it down in a minute. So the second family is when G is of Hermitian type. And what does this mean? This means that there are different ways to characterize it, so that if you look at the symmetric spaces, so it's G, it carries an invariant Kähler structure. You can also say it in algebraic terms. It means that the fundamental group of G modulo torsion is infinite cyclic. And again, you don't need to think about, I don't want you to think about the general statement if you have never heard about this. So let me give you, again, some of the classical groups in this family. So there's the symplectic group. There are orthogonal groups of signature 2n, and there are indefinite Hermitian forms of signature nm. And there's a few more. What? Yes, the symplectic group. So the symplectic group appears twice. SO2 appears twice, but SO2 is actually SL2 cross SL2, so it's not really simple. And SO23 appears twice. But essentially, SO23 is locally isomorphic to SP4R. So essentially, there's one group which appears here and here. And so here we have what is called maximal representations. And I will again shortly in a minute give you a definition for what this is. But I want to write down the two more families. So one here, G is locally isomorphic to SOPQ, indefinite orthogonal groups, where P is bigger or equal than 2 and smaller than Q. And here you have a family of exceptional Lie groups, and there's one real form for F4. One for E6, one for E7, and one for E8. And I can tell you later which real form it is.
But it's not the compact one.
It's not the compact one. So this is the split one. So this is the one, this F4 appears here and there. And these are those where the Dynkin diagram of the restricted root system looks like F4. So this is the way. Okay. So basically what I want to tell you in this, the question I want to address in this talk is, why do we see these higher Teichmüller spaces for these 4 families of Lie groups? And before I do that, I want to shortly, so that you have some example to think about, give you the definition of what the Hitchin component are and what maximal representations are. But then I want to describe, in some sense, characterize them in a different way, which will then, in some sense, give us these other two families. And this is where the positivity appears in the paper.
You're saying there are exactly 4 families?
No. So this is, okay, I would conjecture that there are exactly 4 families, but what we know is that there are 4 families. We know now that all these, a certain class of representation, which I describe explicitly, which have some positivity property, are higher Teichmüller space. So they are discrete and faithful and have tons of other interesting properties. In order to, we can discuss it afterwards, what you would have to show that these are exactly the 4 families. And for this, you should go on the Higgs bundle side of the picture to do that. But this we don't know yet. Okay. So let me perhaps go there and describe what the Hitchin component, how is the Hitchin component defined? And so basically, I already said it. So one way, if I want to give you, you want to give me a connected component of the space of representation of the surface group into SLN, say. The easiest way to do that is, I know how to put the surface group into SL2. Now I put SL2 into SLN, then I give you one representation, and you say, oh, this is the connected component. I take this connected component containing that point. And this is really how you can define the Hitchin component. It's not how Hitchin defined it. So Hitchin defined it using Higgs bundle methods. but it's very clear that this is the connected component you get. So you look at row, let me call this row 0. So you take the fundamental group of your surface, you put it as a discrete subgroup in, you put it in PSL2R, and now you put PSL2R into G, but let me describe it for PSLNR by a particular representation, and what you do is you take here the n-dimensional irreducible representation. Okay, then I have that, and so then I say the Hitchin component of sigma G PSL NR is the connected component of rho 0. Right?
That's a definition.
That's definition. This doesn't tell you anything about its properties. What Hitchin proved is, and this was, it's quite astonishing, that actually this connected component is homeomorphic to vector space, which we know for Teichmüller space. It's homeomorphic to R to the 6G minus 6, and here homeomorphic to R to the 2G minus 2 times the n squared minus 1. And this is quite remarkable, because usually representation varieties have singularities and look complicated. But he didn't prove anything about particular properties of single points in this space. So this is really what Fock and Goncharov and Labourie, I mean Goldman and Choi for n equals 3, and then Fock and Goncharov and Labourie in general proved. So, but let me perhaps write this, this work by Hitchin, so it's R2G minus 2 times n squared minus 1. And you also see easily this is one connected component, because that's the way I defined it.
It's not a definition, it's a notation. You take the connected.
Yes, well, right.
Rho 0 and
Yes.
it's not a concept.
No, it's not a concept. It's just, yes, yes. I call this the Hitchin component. Actually, there is a, yes. Yes. No, there is a, well, we can talk later about the concept which is behind that, but
Right.
that's true. I mean, it's not. Okay, so let me describe maximal representations. And these are defined completely different way. So we have a representation of the fundamental group of the surface into G. Let's take the symplectic group also for.
So in terms of the main theorem is that this component does not contain any representations which are not faithful or discrete.
Yes, and yes.
Who proved that?
So this, for n equals 3, it's Goldman and Choi. And this was right when Hitchin defined it. And it's really by showing that there's they are parametrized by a certain space of convex real projective structures. So it's a very geometric proof. And then for general n, it's Labourie and Fock and Goncharov approximately about the same time with very different methods. So this more dynamical methods. And this somehow writing down positive coordinates, or coordinates, so with relation to cluster algebras, parametrizing a space. And we will see a bit about the flavor of Fock and Goncharov later. So
can one show that no other component of this?
Yes, for PSLNR we know no other component. Does that? Because Hitchin tells us in the same paper where he introduced it that there are essentially 3 connected components. 3 or 6 depending on the parity, but this is, and so there these ones, and then there are the other 2. And for the other 2, you know that in each of these other things, there are things which factor through a compact group. And if you factor through a compact group, you cannot be discrete. Right? So it's, okay. So now, for maximal representations, you have a Lie group of Hermitian type. This has non-trivial fundamental group. So there is a universal cover. You have the universal cover of your group here, and then you have this short exact sequence. So now, if I have a representation, I can ask myself, can I lift it to the universal cover? And there's an obstruction, which for SL2 is the Euler class. So in this situation, it's also this obstruction class that's often called the Toledo number, or Toledo invariant. And let me just, to describe it explicitly, let me shortly remind you that, I mean, we can pick a specific presentation of this group, the one we usually pick. So for each genus, for each handle, we pick two generators, A1, B1, up to AG, BG, and then we have one relation which they have to satisfy, and I mean that the commutator of AI, BI is equal to 1. Right? So now I have my representation, and let's say it sends AI to a matrix AI, and BI to a matrix BI. Then I can start to lift it, right? In order to lift it, I just lift every generator, and then I check this relation. So when I do that, so I call this tau of rho. So this is the product from I equals 1 to G of the commutator of a lift of A and the commutator of lift BI. And what's that? I mean, this gives me something which projects to 1 here. So it means something which lies in the integers. So it gives me an integer. And you might want to convince yourself shortly that, I mean, here I pick a lift, so I make a choice, but as soon as I compute the commutator, it's independent of the choice, because if I make two different choices, they differ by something in the center of the group. So when you do the commutator, it cancels out. So to every representation, I have an integer, and actually this integer is bounded by 2G minus 2 times the rank of the group, so which this is the rank of G, so which is n here. And so maximal representations are those where this takes the maximal possible value. So maximal representations is tau inverse of 2G minus 2 times the rank of n. And so you see, this is a union of connected components because you have a continuous invariant which take discrete values. So it's a union of connected components. In general, it's more than one connected component. What? In general, it's not one connected component, so it has several connected components. And so there's, let me just shortly point that out. So in the case of the symplectic group, we saw the symplectic group appears twice. So we have both things. We have the Hitchin component, which is one connected component. We have the space of maximal representations where we don't know how many connected components there are. And the Hitchin component is contained in the space of maximal representation, and it's a proper containment. So in particular, the situation becomes particularly interesting for SP4R, because for SP4R, there is somehow the standard connected components you have, and then there's a family of connected components which grows linearly in the genus, where every representation in this connected component is Sierski dense. So it cannot come from any construction like we did here, from taking a subgroup like SL2R and embedding it into G. And the other thing, so we know there are many connected components. Also, there's nothing like that. So the connected components, they're not just many connected components, but they are connected components which have non-trivial fundamental group, for example. So it's far from being a vector space. Okay, so let me, perhaps, and also the method, I mean, so this is work we did with Mark Boger and Alessandro Riazzi to show that this actually is a higher rank Teichmüller space, so everything in there is discrete and faithful. And the methods are, again, completely different. So we use bounded cohomology, so very different from these methods. So what I want to do now is describe a characterization of Hitchin components and maximal representation, which really makes them look as the same thing. And in order to do that, I want to introduce a notion of positivity in some flag variety. And I want to describe this notion of positivity for the Hitchin component and for maximal representation. So, and they are. Let me first describe it for the Hitchin component, and again I just describe it for SLN, and not in the general case. I mean, if you know the general theory, you know how to generalize it. So we have SLNR, and SLNR acts on the space of flags in Rn, so tuples of vector spaces consisting of a one-dimensional up to n-dimensional vector space, which are contained in each other.
Maximal flags.
Maximal flags, yeah, full flags. And now I want to, let me describe a bit of this space. So if I fix a basis of my vector space, I can write down two standard flags, which are just given by this basis. So F0 will be the flag where the ith subspace is spanned by the first I basis vectors. And then there's the other one I can define, which is just reading the basis from the back. So where the ith flag is spanned from En up to En minus I plus 1. Right? So these flags are what we call in general position. So they satisfy, so two flags are in general position if Fi plus Gn minus I span my vector space. So this hold for that. And so now if I have a third flag F, which is in general position to F infinity, so I also call this transverse to F infinity, then I can actually write it in a particular way. I can write it as an image of this flag by a unipotent matrix. So then F is U times F0, where U is an element of the lower triangular matrices with 1 on the diagonal. And so now I can use this to make a definition of what a positive triple is. And to do this, I use the notion of totally positive matrices. So let me tell you what this is, or when you haven't seen that. So in general, if you have a matrix in GLN, you call it totally positive if every minor is positive. So you take any submatrix, K by K submatrix, you compute its determinant, it's positive. So in particular, all the entries are positive. The determinant is positive and everything. These have very nice and special properties. So they appear in all kinds of areas of mathematics. They appear in representation theory, but also in statistics. And there's a way to also say what a totally positive unipotent matrix is. Of course, a unipotent matrix is never totally positive in its own right, because you have zeros here, right? So, but you say that unipotent matrix is totally positive if unipotent matrix if every possibly non-zero minor, zero minor is actually positive. And so this is what it is. And so now make the following definition. So you call F0, F infinity, this triple of flags is positive if F is U times F0 with U totally positive unipotent. And so this notion of total positivity, as I said, this is very, for GLN, quite classical. For this general situation of split Lie groups, it was extended by Lusztig to this very general setting. And in some sense, this, to really think of positive triples in the flag variety, this was really one of the main ideas in the work of Fock and Goncharov when they studied the Hitchin component.
Positivity of the minor is in what sense here? So certainly the entries are all positive, but...
Yeah, so pick any minor, so any square submatrix, you compute its determinant. This is positive. So, yes. So, and of course, if you take a subminor, submatrix which lies here, it has to be 0, but otherwise it has to be positive. Yeah. So, let me write down using this notion how you can characterize the Hitchin component. And this is due to Fock and Goncharov. And in the case of SLN, in slightly different language, also Laborie with a complement by Guichard. So if you have a representation, rho is in the Hitchin component, if and only if rho is positive, and I now say what positive means, i.e. there exists a map F from RP1 into the space of flags, where I think of RP1 as rising as, if you want, the boundary of the upper half plane. So it carries the natural action of the fundamental group of a surface. And I want that this map is rho equivariant and sends positive triples to positive triples. So positive triples here, you can either think of them as this is a circle, so you think of them as positively oriented triples on the circle, or you can think of this is a flag variety, and I just gave you a definition of what a positive triple in a flag variety is.
So what are the allowed actions of PSO2R on the flags?
So the PSI2R, the PSI2R acts on the flag if you pick a representation in SLNR. So here you have a representation of the fundamental group of the surface into SLNR. So this is this gives you the action on the space of flags. It's not necessarily an action of PSI2R. If you are at a point in the Hitchin component which does not preserve a copy, it does not contain in PSI2R, you will not have a natural action of PSI2R here necessarily, but just of the fundamental group of the surface. But why is essentially, how do you prove this? How would you go about proving this theorem? You take the point which defines you the Hitchin component. You show this is positive in this sense. And so this in particular means that the embedding of the circle, which is invariant under this SI2R, is positive in this sense. And then you show that this is a property which is preserved under deformation and is also defined to a closed subset, right? Like this. Okay, so let me now describe here the corresponding thing for maximal representations shortly, and again for the symplectic group only. So here we take a different flag variety. We look at the space of Lagrangians in R2n. So this is not the full flag variety, it's a partial flag variety. So I do now just a similar construction. So if I fix a symplectic basis, I get one Lagrangian by taking the span of the EI, and I get another Lagrangian by taking the span of the FIs. And if I have a third Lagrangian, which is transverse to L infinity, so such that these two n-dimensional subspaces span my vector space, then, so let's write this transverse to L infinity, then I can write L as n times L0, where n lies in this subgroup. So this is the unipotent part of a stabilizer of L infinity. And by the Lagrangian property, this n actually has to be a symmetric n by n matrix. And now
Ones there are identity, n by n identity matrices. On the diagonal, those are big identity matrices, right?
these are big identity matrices, yeah. Exactly. So now, well, we can use this to write down the notion of positive triples. So we have L0, L infinity, write L as n times L0, right? And now we have n is of the form 1, 1, n, where n is symmetric, and we require this to be positive, definite, symmetric. And not just symmetric matrices, but positive, definite, symmetric matrices. And then you can write down characterization of the space of maximal representations in a completely analogous way. So you say this is representation is a maximal representation if and only if it's positive. So where we require that we have a row equivalent map into the space of Lagrangians, which sends positive triples to positive triples. And so from this point of view, we have these two quite different notions of positivity in flag varieties, but with this notion we can characterize them in precisely in the same way. And so,
Sim plus, what does that mean?
Positive definite symmetric matrix. So now you, let me put this here. So now you can ask yourself if you want to use,
Wait, so the
yes?
flag is, I mean, this Lagrangian thing is positive, it's different.
The Lagrangian?
Lagrangian?
Just Lagrangian Grassmannian.
Just Lagrangian Grassmannian.
No. What does it mean to be positive there?
So this is what I just defined here. So a triple is positive if it's basically if it's up to
Positive triple. Oh.
of Lagrangian. So you have. So I can give you two ways to say it. So I want, if you say it this way, it's up to conjugation by up to the G action. You can send this triple to the standard triple L0, L infinity, where L is the image of this positive definite symmetric matrix of L0. There's actually using other, you can also say it in different terms. There on the space of Lagrange, you have the Maslov index, and it's equivalent to saying that the Maslov index of these three Lagrangians is n. But I don't want, I wanted to highlight the similarities with this other notion. So now, so you can ask yourself, okay, so looking at it from this point of view, these things look like the same thing, and the key property is that you have this notion of positive triples, of positive triples in a certain flag variety. So you can ask yourself, when do you have this? What are the other groups? You have that. And so let me say as a definition, so I say G, if I have a simple Lie group, has a positive structure with respect to a flag variety. Variety F, if there.
Makes sense. What is that? Oh,
yeah, I define it now. So I just say, basically.
Which flag, what does it mean to have a given group? What do you mean by flag?
What do I mean by flag variety? So, with different ways to say this. So, one is you can say a flag variety is a boundary of the group in the sense of Furstenberg. So, it's really a homogeneous space with its G modulo P, where P is a parabolic subgroup. So, if there, let me say, if there exists an open semigroup in the unipotent radical U of P. So what I want to essentially, what I say, when you can define what is a positive triple by the same definition where you replace, I mean, this will always be in the unipotent radical, and you want there's a specific open and sharp semigroup, which define that. So then what, when you come up with, and this is in some sense not the definition you write down, but it's an equivalent characterization, then you can show the following theorem.
So is the parabolic actually necessarily determined?
Yes, so this,
one possible?
no, there are at most two. And so this is drawing work with Char. So G carries a positive structure. And here we have if and only if. It belongs to these four families. So this is the list. This is where this list comes from, and you have to be a bit careful. So this is, here you have to add of tube type, and this will only have SUNN. So I can shortly write down what, I mean, so in each these cases, the flag variety is determined. And in order to write this down, let me remind you, if you know that the parabolic is, choice of a parabolic is determined by a subset of the set of simple roots. So if I call delta the set of simple roots, I just want to write down what the subset theta determining this parabolic is. So in the first case, it's just the min-minute parabolic. So this is theta is the entire subset of simple roots. So that's what we saw for the Hitchin component. It's a full flag variety. In this case here, is the other opposite case. Theta consists of one element. And this is what we saw for the space of Lagrange. It's a maximal parabolic. So it's, in this situation, theta is the complement of one element. And in this situation, I mean, here you have four roots, and theta consists of two of them. And you can, I mean, you can exactly write it, I mean, read it off of the Dinkin diagram. So what, so how did we, from this theorem, get to the theorem I stated in the beginning, that you have higher Teichmüller spaces for these four families of groups, is by looking at the following. So if I have a positive structure, right, I can look at positive representations in this sense. So representations where I have a map from RP1 into my flag variety, where I have this positive structure, which is row equivalent and sends positive triples to positive triples. And then what you prove, and this, I mean, prove with Guichard and Laborie, and then there for SOPQ, there's also work of Beira and Pozzetti, and we are currently finishing a preprint with the 5 of us, which gives us the very, very general statement. So, and let me write it this way: the set of positive representations positive of sigma G into a Lie group G, which carries a positive structure, is a higher rank Teichmüller space. So there are two things you want to prove here, or two things you have to prove here. First, that if you have a positive representation, you are discrete and faithful. There's one thing you prove, and then you want to show this is a connected or union of connected components. So you also need to show that if you look at the set of positive representations, it's open and closed. And open is easy, closedness is hard. And in order to prove the closeness in the general case, what you actually prove is a generalization of the color lemma. So in hyperbolic geometry, there's a Collar lemma, which essentially states if you have a hyperbolic surface and you have one curve which is very short, then a curve intersecting it has to be very long. And so here you prove somehow generalization of this statement for if you have two elements of the fundamental group which have non-trivial self-intersection, then the length measured, you have in higher rank many ways to measure length. The length measured in an appropriate way of this curve, and the length measured in an appropriate way of this curve. If this is short, this has to be long. And what it gives you is that if you have a limit of positive representations, in the limit you still remain transverse. And you can show that then it has to be positive. So I want to stop here, but I want to say one thing that, I mean, this is why we originally set out to look at these positive structures, to find an explanation why do we see these families of higher Teichmüller spaces, even though they come from very different techniques and very different methods are applied. But this generalization of, I mean, you get this generalization of total positivity, which is, I think, very interesting in its own right, because it suggests, creates a very suggestive picture and opens up several conjectures which have nothing to do with surface groups, but with other things, cluster algebras, non-commutative cluster algebras. There's also, I mean, for Hitchin components, there's a very compelling connection with theoretical physics, which we don't have in these families 2, 3, 4, but I mean, where this picture suggests that there should be something in these other families as well. There are relations to quantum groups which are suggested by this picture. So I think it's very interesting, far beyond just looking at representations of surface groups. It also predicts some things about the dynamical properties of these groups, which you wouldn't come up with somehow before, but which we can prove. So, and let me just say one last thing here. So if you think of this example, I mean, this is really determined by one root, and a lot of the combinatorics you see is like the combinatorics you see for SL2R. So somehow this picture suggests that there's a way to look at these groups as somehow groups of type SL2R, but not defined over R or C, but over the matrices, n by n matrices with coefficients in R or C, or more general coefficients. And some part of that we can now make very precise. And when this refers to when you implement it, what it really gives you is that a way of looking at the Siegel space, for example, for the symplectic group, as a kind of non-commutative hyperbolic plane. And I think that there's up to trace identities for the symplectic group, which generalize SL2 trace identities from SL2R to this more general group. Yes? So
I can't relate the definition and the theorem.
The definition and the theorem.
I mean, I don't see why, if I look at the theorem by itself, I don't see a theorem there.
So once I have this positive structure, and this is something I can define what I mean by a representation to be positive. Yeah. Because I can say, okay, so I want this boundary map from RP1 into my flag space where I have.
That's what the definition means.
Yes, and this is what, I mean, so these are all the representations which are positive.
Yeah. See.
But I think you're done, so we should first applaud, and then you can ask a question, right? Normal time. No. Applause first, then questions.
First is the concept of G has a positive structure.
Yes.
That means there has to be a flag variety where there exists an open sharp. I don't know what sharp is.
So that the inverse, I mean, if you have an element in it, the inverse is not in it.
Oh,
so.
And the unipolar triangle, okay.
So once you have that, you can define what is a positive triple. Because I just say, I mean, I have this open semigroup, let me call it U+, right? And so if I have an arbitrary flag tuple f0, f infinity. I can write f as u times f, 0. And now it's always, I can always write it as u times f0, where u is in u, right? But now, when I want to call it positive, if I can do this with u in this u plus.
Which is what the definition asks for?
What this is, the definition tells you you have an appropriate u plus, which has the structure of a semigroup.
And then the set of positive representations is now defined.
Yes.
And then it has all these nice properties.
Yes.
Three groups.
I think you just
Good.
indicated.
Yes, I'm done. So thanks. That's fine.
So any questions for Anna?
There's bad information being transferred, and I don't
Any
like
questions?
Mr. Last.
So, what is the status? So you said so far that you have that for these four families you have such components.
Yes.
How far are we from knowing that?
This is all the cases?
Yes.
So, so there's one case which, I added this tube type here, and we also have components, this is not of tube type, but they have this particular, every maximal, this is one other thing we proved many years ago, every maximal representation in a non-tube type group sits in a tube type domain. So there's this little bit which we know, which is more than that. Then there's, this we know, this we can handle. Then what you really need to prove, what you would have to prove to show that these is all, is that for any other connected component than these which carry a positive structure, you find a representation with factor through a compact group. And for this, one should really use, the right approach, I think, to do that is use methods from the theory of Higgs bundles. So what we already know from the theory of Higgs bundles, we get a parametrization similar to Hitchin's parametrization of many of the connected components of this positive, conjecturally all. But again, we don't know when that is all. And so what, for this, when you look at the side on Higgs of Higgs bundles, you have the Higgs field to do Morse theory on your space of Higgs bundles, essentially. So this is why they can say a lot about connected components and also topological type, homomorphism type, or homotopy type, at least, of the connected components. And so basically, you should use these methods to try to show that in all the other cases, you have connected all the other connected components you factor through a compact group. And this would answer, if you could show that, it would answer this question. It would also answer another question, which, I said for complex Lie groups, when you look at the representation variety, we know its connected components are distinguished by characteristic invariance. For real Lie groups, this is not true. And all the examples, we have a lot of examples, named those. Whenever you have a higher Teichmüller space, basically there's another component which has the same characteristic invariance, but where things factor through a compact group. Because, characteristic invariants are seen by the compact group. So what this would also give, which, also I think conjecturally I would believe that this is true, that you have this additional connected component for representation into real Lie groups only in these situations, when you actually have these higher ranked Teichmüller spaces. And in all the other cases, these are the other cases we know they are distinguished by characteristic invariance, actually. So this, but it's, with geometric methods, you cannot attempt, I think it's really out of reach to prove anything like that. With Higgs bundle method, I think you have a chance to look at the minima for the Higgs field and try to show that there is a representation through the compact group.
I want to paraphrase the last term. It's got this phrase, higher Teichmüller space. It sounds cool, but I don't know what it means.
No, it just means that, here it just means it's a connected component. It's just to have a shortcut, right? Here it just means these form an open and closed subset of the representation variety. this one statement. And the second statement is every representation in this is faithful with discrete image. So these are the two, actually, this is the content of the theorem. There's a little bit...
Closed discrete.
Yeah. There's a little bit more than what you can say, but I mean, this is really the content.
So maybe this is wild and off topic, but I mean, in the case where G is a Hermitian type, you have this group acts on a Hermitian symmetric space, and now you can take a quotient of that Hermitian symmetric space by the representation. Is there any interesting relationship between holomorphic curves in that space?
This is, I mean, something, I mean, we know very, very little. So this is, I would say, we know a lot of, if you take whatever somehow hyperbolic picture on Teichmüller space, we know a lot with that generalize. I mean, we have now many results that generalize. Whatever complex analytic picture, in some sense, question about we have essentially no idea how to generalize it in this picture. So, I mean, in this situation, there's some example where you can show, okay, so these quotients will not be Stein manifolds, or they will be Stein in very specific, there's one example where you have a holomorphic, where you start by having a holomorphic curve, essentially, but it's not very well studied. What we know a bit about is, for example, these will be infinite volume quotients. So we know a bit about compactifying these quotients. We know a lot about geometric structures associated to those, and they partly, by constructing domains of discontinuity and taking quotient manifolds, and but about the complex, sometimes these questions, it's very hard, I think. But I think it's very interesting to try to say something.
Okay. Hang on again.